Software Central. I take this opportunity to introduce you all the speaker, Mr. Rajkumar R. Mr. Rajkumar R graduated as Electrical and Electronics Engineer from Anna University, Chennai. Currently, he is designated as Senior Application Engineer in VI Solutions, Bangalore, and handling the major responsibility of supporting various industries in implementing several turnkey systems and system integration projects using NI products. He is also handling the major responsibility of improving the quality of engineering and science education and eradicating the impoverished methods of education and inculcating the interest for the lab view. He is also a CLD certified and has traveled far and wide throughout India and has delivered thought-provoking lectures which inspire the students and kindle their interest towards LabVIEW, and has also visited 35 plus engineering institutions. He has conducted more number of hands-on trainings to the engineering students of various branches on LabVIEW basics and data acquisition. He also has conducted many faculty development workshops on various trending technologies, including embedded and control design, image processing, etc. He has delivered 50 plus lectures on experimental engineering education on varied topics. His key interest areas are measurement and automation, sensors, data acquisition and signal conditioning, FPGA-based embedded system design, and power electronics. I welcome you, sir. I request all the participants to use this opportunity to gain knowledge from Mr. Rajkumar R and make the session more interactive and interesting. Thank you all. Over to you, sir.
Yes. Thank you very much, ma'am, and thank you everyone as well as the ACS College of Engineering for the warm welcome. It's a privilege and honor to be a part of this FTV program. I hope this FTV program would be fruitful with respect to knowledge transfer as well as knowledge gaining, and I hope I will be giving a lot of insights as to how the systems whatever we are going to see right now is going to be helpful in the development of the global technology which can be developed by us. So thank you once again for the warm welcome.
Thank you, sir.
Yeah. So with that being said, as already ma'am has introduced very well, my name is Rajkumar Rajshekharan. I currently work as a senior applications engineer at VA Solutions Bangalore. So VA Solutions is a test and automation company which is located in Bangalore. We service several of our both government as well as non-governmental organizations with test and automation solutions using a tool called as NI LabVIEW. We are also system integration partner of National Instruments, okay, the company which is the creator of the tool, a very famous tool for engineers and scientists around the world called as NI LabVIEW, and several other OEM products from the hardware-based OEM products from them. So we'll be seeing about that, so that in a detail. So I believe I think yesterday a lot of insights would have been given by one of my colleague, okay, about the same tool. Today we'll be seeing about how we can enhance the effects of LabVIEW not only as a true software, okay, but how it can help as a hardware, right? So let me just share my screen and let's kickstart this program. Okay, so let me share my screen. Yeah, so sharing my screen. I hope the screen is visible.
Yes, sir. Now
Yes,
it's
sir.
coming.
Yeah. So today our objective is going to be talking about how we can use the um, the software and the hardware, okay, to implement certain aspects of industrial IoT. Okay, and what are the important components which is to be developed, designed, and tested, okay, and to be implemented using the systems available, right? So already you might be aware of a tool called as Lab yesterday. I think my colleague would have explained. Using that, tool, how we can talk to several hardwares. Okay, how we can collect the data, bring it into the software for further analysis, and not only for further analysis, how we can communicate the data over a brief area. Okay, when I say brief area, the data should be available across the globe by the shareholders who are interested in such data. Okay, I'm sure everyone would be knowing very well more than me about what is IoT and IIoT systems. Okay, how it is impacting the technology growth all around the world, and what are the use cases. Okay, when it comes to IoT, how it is impacting several factors. Okay, of technology. So, and if you see IoT, okay, we have both industrial and consumer based. So both of them are available. Okay, depending on the end user, okay, we might classify two types of IoT, and the use cases are going to be pretty much, you might be aware that, if you take industrial IoT, it involves smart factory, where we will be able to monitor from end to end, from production till delivery of the products or services, whatever deliver, we can monitor the aspects of the same. Smart grid, okay, how we can, collect the data, how we can collect the data and modify, grid values, how we can, check for certain aspects of, the health of the grid. Okay, all these things can be monitored. Essentially, you can monitor the parameters in real time and transmit them across the globe. Not only data transfer is possible, even decision making, okay, by using advanced clouds, which can run very complex deep learning algorithms to, identify certain patterns, can also be achieved. The data analytics can be done, right? So same thing can be done in commercial as well, okay, consumer based. So where you can have, as in systems like wearable technology, smart TV, smart appliance, smart home automation, that comes under that, right? So this is with respect to industrial and general Internet of Things. But in the domain of NI technology, where does this apply? So when it comes to NI technology, we talk about industrial Internet of Things primarily in two cases. Okay, we talk about industrial Internet of Things for condition monitoring. Okay, when I say condition monitoring, we'll have a lot of machines which are running, and in order to monitor the health of the machine, in order to know when exactly it's going to fail, okay, we do something called condition monitoring. So that is just passively monitoring. But by using IoT, transferring the data to a complex cloud, collecting data over a period of time, we'll be able to do something called time series analysis. Okay, we'll exactly able to estimate when the point of failure is going to, be attained. Not only will we able to get the exact timing for point of failure, we'll also get a timeline. Like when we talk about motors, okay, we'll say when is it going to start to heat up, when it is going to produce certain vibrations, when are we going to get noise, due to constant running, and when are we going to get total failure. Such type of, complex predictive maintenance can also be done. Okay, but of course, in order to achieve this, we need to have very large amount of training data. Okay, we need to collect a lot of data over a period of time, then do a training of it and deploy the model in the cloud. Right. So for that, we have a lot of data scientists, and all of the people will be in case of that. Right. So and microgrid communication and control. Okay, so a lot of these microgrid, communication and all these things will be running in a very long distance, location. And in order to monitor this, okay, we cannot deploy a professional, okay, wanted to monitor the status of this. So we need to do certain, you know, um, remote monitoring capabilities, okay, embedded capabilities which can monitor these values 24/7. Okay, we need to have an embedded system smart enough to do that. Okay, and this data should be available globally so that any stakeholders, okay, it could be a design team monitor evaluating whether the design deployed is working properly, or the stakeholders from corporate, okay, if they want to evaluate whether the uh, the unit is working properly, it's generating revenue. Okay, it's not having any downtimes. Okay, what is the cost of the downtime? How when to schedule the maintenance? So all the levels of people can monitor this data, and in their own language as well. When I say language, it's not like for communication purpose that language. Okay, corporate will have different language, system engineers will have different language, scientists will have a different mode of communication. So you can view the data as far as the stakeholder is concerned. So what are the recent trends in IIoT? Okay, what are going to be which we are going to expect in the rising future? So when we say about that, the evolution of communication technologies. Okay, right now, if you are all aware of 5G is going to launch. Okay, more than how the 5G is going to be useful in you know commercially, okay, industry is very much um, excited, okay, you can say, for the implementation of 5G. Okay, when they say it's going to have a lot of capabilities for real-time monitoring. Okay, since data speeds and throughputs are very the data speeds are high, and the latency of data communication is also very small. Okay, so we can expect this to be used in several industries, okay, which could be used for condition monitoring, remote monitoring, asset monitoring. Okay, so that places it could be used. And industrial automation. Okay, several robotics, monitoring and control. Okay, which needs to have real time, capabilities. So since 5G offers such, very less latency, this industrial automation control could be done from anywhere over the world, and can also be automated from anywhere over the world. Okay, so a person who is programming this, okay, need not necessarily be in the same country. Okay, they could be from anywhere. They could be anywhere, or access this industrial automation tool and deploy the code which is necessary to run it. Okay, so it has made this much simpler now, and that's what this gives us the plenty of opportunity for remote monitoring and operation, right? So in this case, okay, we need to understand what is the architecture for IIoT. Okay, I'm sure you must be very well aware of what are the steps involved in the implementation of IIoT architecture. Okay, and when we talk about that, okay, we start with edge devices. The edge devices are the field devices, as we call it. Okay, it's going to be responsible for collecting the data and transmit them over to cloud, and that will be a separate device. Okay, so here edge device is going to be typically in low powered, very small device. Okay, just capable of connecting to internet. Okay, predominantly it will be having capabilities of collecting data from sensors. Okay. Ideally, a low cost microcontroller will be preferred. But internet connectivity, either direct or indirect internet connectivity, should be possible. Okay, so that is going to be the edge device. So in commercial entity, smart device, if you say smart wearables, okay, so which will be, if you see band is available now, okay, it will collect important parametric data of our health. Okay, maybe heartbeat, maybe the stress level, okay, maybe ECG data. Okay, could name a few. This data is transferred over to your device through Bluetooth Low Energy BLE 5.0. Okay, so that is also a connectivity option, right? So depending on the context, okay, you will have edge devices available, and that data is going to be connected to cloud through a connectivity option. Okay, again, you have plenty of options when it comes to that. You have GSM, Wi-Fi, LoRa, Sigfox. Okay, so GSM is basically typically, everyone knows about GSM. Okay, it started with 1G, 2G, it has several, uh, you know, generation, right? And Wi-Fi is basically local internet connection. Okay, wireless internet connection is established. So this is typically it goes through cell phone towers, and this is going to be intermediate platform which is available everywhere. I hope everyone knows about that. Yes. So what is going to be new is going to be very specific to IIoT systems, that is called LoRa, okay, and Sigfox. Okay, LoRa is also a radio frequency data transmission system. Okay, ideally used for IIoT, or IoT platforms. Okay, so it's going to be unlicensed data transfer, and it's going to be out of this bands of GSM and Wi-Fi. Okay, so from the LoRa or from GSM and Wi-Fi or whatever it is, okay, it's going to be connected to the World Wide Web, right? And from there, it's going to be sent to the cloud. And cloud is going to be any cloud could be accessed. Okay, so depending on your availability and even depending on your knowledge of the cloud, okay, how you're going to access the data. Okay, so it's going to be available. So AWS is one famous cloud which is available. Okay, so which is also capable of running AI. Okay, but there are plenty of other options are also available. Okay, today we'll be showing one such option which is free to use, and it could be used to transfer data and receive data anywhere, right? And just transferring data is not useful. Okay, we need to be able to observe the data from anywhere over the globe. Okay, once we put in the cloud, we should be able to observe the data anywhere from anywhere. So we have front end, devices here, right? So front end data could be, your PC, or it could be mobile edition, or it could be as simple as a notification when certain parameter which you're collecting is going to exceed, the data which is expected. So first we are going to discuss about thing, edge device. So before that, if you have any questions, please feel free to ask. Okay, you could either unmute and ask the question, or you could just pop the question in the chat box. Okay, I guess there is no question. So if you have any, you feel free to please put it in the chat box, and I'll be able to clarify it to you. So in this first, we are going to talk about edge device. Okay, when I spoke about edge device, the one important thing what I spoke about is the ability of edge device to collect data. Okay, so collecting of data, okay, we call it as data acquisition. So we are going to talk about what is data collection, how to acquire data. When I say data, in what context do I mean data? Okay, when data right now is so commonly used, even user information is also data. Okay, in terms of very generically usable, um, you know, software engineering. But the type of data what we're talking about is, we are talking about data like temperature, pressure, so parameters or phenomenon, whatever you're measuring. A sensor measurement is what we call it as data. So how to collect such data from edge devices? So there are several things available. Okay, type of things available. You could talk about data, for things. Okay, in industrial terms. Okay, it could be used for several, uh, usage. Okay, so I typically, as I told, LabVIEW is used for test and automation. Okay, we conduct tests for electronic, components. So in order to conduct the test from all over the world, people use NI products to conduct tests. Okay, and with the element of IoT, you can conduct this test from anywhere over the world. Okay, so now that machine which is conducting the test is going to be Think, a production equipment. Okay, when you manufacture huge amount of components. Okay, so each and every item, whatever you test, we are producing. So that is going to be now a thing. I mean, the machine which is producing, which is doing that job is going to be Think. So the production equipments like part handling machine, packaging machines. Okay, how much per day it's packaging, whether any faults have occurred during the packaging. Thousands of things could go wrong. Operational assets. Okay, this is what I told as example before. Okay, pumps, motors, asset monitoring system. Whether the asset is doing its job properly, whether the asset we are monitoring is going to fail in a few moments. Okay, and a lot of other information also needs to be observed. Okay, the assets which we monitor is, we can say, pumps, motor, turbines, okay, grid devices, okay, transformers, transmission lines, and other compensation devices like in fax devices. Okay, so these are also these all needs to be monitored continuously. And transportation and heavy equipment, okay, tractors and combines, okay, when they are going to fail, okay, basically automotive units. So sensors and actuators. So first thing what we need to understand is what are the sensors, and I'm sure everyone knows about what sensor. So sensors are components that are going to convert this physical information to electrical information. There are different types of sensor available. Okay, so first very important thing in thing architecting is sensors and actuators. Okay, so different types of sensor uses to sense different elements. But before we select a sensor, we need to understand what is required to be observed from an IoT device. Okay, what information do you need? What do you want to understand about the information surroundings? And what are you going to get output out of it? Okay, do you just want to observe the data, or do you want to process it further? Okay, what do you want to react further? Okay, these are the kind of information you need basically. Okay, and when you talk about IoT device, okay, industrial IoT at least, okay, these are the five important things you need. First is you need to have a edge-ready hardware. An embedded system is capable of acquiring data, okay, 24/7, as well as reliably. Okay, it should not have any, it should not crash out of the blue, and that would be like downtime should be very less. So maintenance also should be very properly managed, and data transfer should also take place reliably. And we should be able to do control. Okay, to explain robot if you're controlling. Okay, we need to have a very steep control curve. Okay, it needs to be easy to control and quick to control. And open connected software. Okay, when I say open connected software, okay, it doesn't mean open source. It means that it should have a very easy to use environment, and it should be able to access most of the features available in the hardware. Okay, that's what it means, open connected software. And data acquisition from sensor. Okay, when we talk say sensor data acquisition, most of people will be like, the sensor will give voltage value, and it will in order to convert back to physical phenomenon, just simply do it. Okay, that is not the case. Most of the time, excitation, um, non-linearization, linearization, and lot of other calculations needs to be done. Okay, something called a signal conditioning is very important, right? So these are the things which we need to consider. So how to do this without, in order to bring the signal conditioning circuits like excitation circuit and all those things, a lot of engineering needs to be done, okay, most of the time. But how to reduce the engineering required from our side and go forward to implementing such systems with minimal either both programming knowledge as well as hardware design knowledge to design a system of IoT, right? So to implement a edge device, okay, we have an option to go for a data acquisition device. Just give me a moment. uh, just a moment. Yeah. um So we need to be observant about for implementing data acquisition devices. Okay, so data acquisition is it's a set of devices, okay, used in industry to collect important data for, you can say, for troubleshooting or for monitoring, okay, or for testing purposes, right? So depending on the scope of our project, whatever we work, okay, we need to understand what type of data option device we use. Okay, there are plenty of options available with many of the vendors, okay, but the point here is to reduce the engineering point from our side, okay, to design our own, data collection unit. Okay, rather it's best to go for an existing factor. So we have a lot of options here. Okay, depending on the scope of project, maybe we need thousands of channels to be acquired. Okay, maybe we need to acquire, only few channels, but we need to have certain signal conditioning already available. Or maybe sometimes we just need to collect voltage data, and it should be portable. Portability will be an option. Sometimes we need to just we need to have a lot of channels, but it just needs to be connected directly to your PC's, uh, motherboard itself directly. So depending on the usage, you have a lot of options here. Okay, so typically in an industrial environment where you want to acquire thousands of, data, okay, we will be going for a high-end device such as PXI devices. Okay, so the point here is to collect data, we have specialized systems available for it. Okay, so what is this data action device? Okay, so DAC devices are, devices which is used to collect data from external world, from the sensors and actuators. Okay, convert them to digital, information, and send it them to your computer for further analysis or recording. Okay, there are several, form factors available for it. Okay, we have USB based, PCI bus based. Okay, that is to directly to your motherboard you can connect them. Or sometimes we'll be having it as a PC based, data ocean unit. So there are plenty of options available to collect data. So it will have something, a flow, something like this. Okay, a sensor or actuator. Next will be, DAC device will be there, a hardware will be there, which will have a signal conditioning unit. The signal conditioning unit is essentially to, the sensor data might be very low voltage, okay, or very high voltage, or very high frequency, or maybe it's in a industrial floor, okay, which can have a lot of noise. Okay, so in order to convert, I mean, your ADC will be having a limit as to how much voltage it can acquire. So in order to convert whatever data we have into something which your ADC can acquire, we'll be having intermittently a single condition unit. Okay, if the voltage level is low, we'll be having an amplifier. If the voltage level is too high, we'll have an attenuator. Okay, if it's very noisy, unit, okay, we can have a filter. Okay, then it can be a digital filter inbuilt, or you can build an RC circuit outside. So all this needs to be considered in the DAC device will be considering for. And once the signal conditioning is done, okay, for different sensors we'll have different types of signal conditioning, which we'll be discussing. Then later part, you'll be having analog to digital converter, okay, which will convert whatever data you acquired to the format which your computer can understand. And once that is understood, okay, you will be having a bus over here. Fine. So bus is basically that device needs to push this data to your computer, right? That bus connection could be a USB based connection, or as we discussed, okay, we have several other connectivity options available: PXI, PCI, even Wi-Fi. Okay, a lot of other options are also available. And when we talk about sensor data, okay, we have analog and digital. Okay, so that we already know. And when we talk about sensor information, okay, we have a lot of phenomena available. Okay, we speak about temperature. In temperature itself, we have different types of temperature sensor like thermocouples, RTDs, thermistors, okay, to name a few. And to this day sensors, okay, we'll be having options like what type of signal conditioning is to be inputted. So it will differ among everything. So for each and every phenomenon, you'll have different sensors, and for different sensors, we'll be having different capability, I mean requirements for signal conditioning. Right? Either you can, if you have engineering capabilities, you can design a circuit which could signal conditioning you can design, and which should convert it to something your ADC can accept, or you have to go for an existing, already tested and tried solution. Right. So NI offers such ready-made solutions for us to acquire several types of signal conditioned data ocean units. Okay, now we are going to see how to design such systems. First, we are going to see what is data acquisition in with respect to in a LabVIEW, and how to work with it. Next, how to collect sensor data from it, how to display the data, what are the software which is required for us, and how to push such data to cloud. Right. So if you have any questions, please let me know. Okay, I feel that there is no questions, so I'll just proceed back to uh, so what provokes us to select a DAG device? Okay, to select acquire data from external world, what are things to consider especially? So since we'll be working with sensors, some sensors will also output voltage, current, or some will output DI, digital output. Okay, so you have to first consider that is whether it's going to be a voltage based output or current based output, or just true or false. Okay, or either sensor based, whether you're going to acquire it from a thermocouple or accelerometer or strain gauge. Okay, so depending on that, you need to use an appropriate signal conditioning DAC device, right? Or whether we're going to control something. Okay, whether we need to switch on and off LEDs or sometimes motors. Okay, so different types of motors will have different type of drives. Okay, so we have to understand about that as well. And sometimes we'll need specialty IOs like protocol based IOs. Okay, maybe you are working in automotive. Okay, so automotive requires connection to CAN bus, okay, called control area network. So in order to interact with that, you need to have a specialized hardware. So these are all the considerations which you need to understand. Whether you need to go for say the voltage based value or current based measurement or just DIOs or whatever it is. So an example here is, let's say you are going to design an in-vehicle data logging device. Okay, you are going to conduct tests on automotive vehicle. Okay, so when you talk about that, if you see a typical data logger, okay, if you're going to test the the engine, okay, and other aspects, okay, we'll be having analog input and digital input and output and specialty. Okay, so in analog input itself, we'll be having different voltage levels. Okay, maybe you're going to measure voltage levels up to battery voltage levels you're going to measure. Okay, so 12 volts measurement, 10 volts measurement, and 60 voltage measurement, right? So and several other sensors like thermocouple, you want to measure temperature at different points, and accelerometer data. Okay, you want to measure vibration at different places. Okay, strain gauges, torque sensors. Okay, to name a few. And DIOs. Okay, you want to measure how fast the car's motors, some of the motors are running. Okay, you want to use encoders. Okay, so that is going to be, basically the encoders are going to give digital pulses. You want to measure them, right? So in order to do this from scratch, okay, you need to have significant amount of engineering effort available with you. Okay, instead, you can go for a ready-made application, ready-made, units which can measure them. And these are all to be measured by us. And there will be some other embedded system which is available inside the car itself, which will be measuring them already. And typically, we need to, in order to validate that only, we will make a separate measurement with a standard device, and we also collect data which is measured by the device also. Okay, the device is inside car, so that will be that information will be got from a unit called CAN bus. Okay, CAN is basically an internet inside the car itself. Okay, to communicate between certain subsystems. Okay, we will be getting data from that as well. So that is also data only that will be acquired by us. So these are systems which we need to consider. Okay. There are other things like how to select the DAC hardware and what are the types of data DAC hardware available. But let us not get very deep inside that. Okay. So three key factors will decide. Okay, the important factors will be resolution, range, and rate. Okay, resolution is basically the ADC's resolution. And if we have already learned about ADCs, okay, so in order to select ADC, we need to understand how precise you want to acquire the data. Okay, do you want to acquire even a microvolt change in voltage you want to log? Okay, or if it's not much required, then how much is required? So before that, you need to understand what difference it makes. Okay, so this is the difference. If you see resolution between 3-bit and 6-bit, okay, for an acquired sine wave, you can see the 3-bit resolution um, observes very poor, observation of a sine wave. Okay, when it acquires the pure sine wave, okay, it observes it such something like a staircase, because it cannot differentiate very large amount of very. I mean, it has a very less accuracy, you can say, right? It cannot differentiate between very small voltage. It has a very large voltage points. Essentially, when you say 3-bit resolution, it has only 8 variations. Okay, 0, 0, 0, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, like that. It has only 8 variations. Okay, and which means then it will not be very accurate. Okay, you can say sensitivity will be very less, right? So the more high the resolution is high, okay, the more accurate the representation of signal will be. If not, it will be less. Okay, range also, if you see, and if you see, let's say if you're talking about acquisition of data from a sensor, we need to understand what will be the output range of the sensor. Okay, whether it's going to be plus or minus 10 volts, or whether it's going to be 0 to 5 plus or minus 5 volts, or maybe it's going to be plus or minus 2 volts, 0.2 to minus 0.2. Okay, or it's whether it's going to give 60 volts, 200 volts. Okay, so that is going to recommend the voltage range, whatever you're going to measure, and how fast we are going to acquire. Okay, sampling rate, which is basically defined by Nyquist theorem. So these are the critical factors which define, okay, what hardware to select. So even though there are hundreds and thousands of options available across the industry, products, and inside NI itself we have several options available. Okay, now in order to make the learning much simpler, okay, we are going to use a simplified version of a DAC hardware, okay, just to acquire data from real world. So we are going to use something called as NI MyDAC. So which is essentially a student version of a DAC device. Okay, it offers the same operation which is to be performed by the DAC device across the industry, but it has very small amount of, you can say, IOs, but it is very well equal to capable of, a DAC device industry as well. Okay, of course, it will have certain trade-offs, but it will, have the capability of acquiring and generating, you know, data ocean capable signals required for industry as well. Okay, so we're going to be talking about NI MIDAC. So MIDAC is essentially a USB based device, okay, which has the capabilities of a USB DAC, and it will have certain IOs inside it. Okay, apart from that, other experimental IOs are also available. Okay, if you want to perform certain experimental, data, like for example, you have a if you want to do audio synthesis and audio analysis. Okay, you have a audio input and output as well. Okay, if you want to make medium voltage measurements up to 60 volts, if you want to measure, you also have a DM on board it. And if you want to, other IOs are also available. Okay, I'm not sure, some colleges will already have MIDAX with you, some are already familiar with that, but this is what is going to help us make measurements. And the good thing about this is, in order to program, in order to acquire data and generate data from this particular platform, we don't need to learn complex hardware-based programming language, because this could be used to, not to interact with this. LabVIEW alone is sufficient. Okay, because the point of LabVIEW is not only to be only graphical, it has capabilities to acquire data from such hardware and visualize it in a very easy to understand manner. Right. So it has a very generic, analog input. Two analog inputs are available. Two precision analog inputs are available. Okay, two analog outputs are available, and 8 DAO channels are available. Meaning it could connect to, potentially it can acquire 8 digital sensor data or can control 8 relays. And it also has certain excitation voltage like 50 plus or minus 15 volts plus 5 volts is available. And on top of that, you don't need to supply separate power supply for that. It's USB powered. Okay, USB bus powered. Okay, you can just connect it to USB and work with it. And it has certain specifications like 200 kilo sampling rate. Okay, meaning according to sampling rate, if it can sample 200 kilo samples per second, it is capable of doing up to, it can acquire frequency information up to 100 kilohertz. Okay, so if you want to sample something of 100 hertz, you need to give at least greater than twice, okay, according to sampling rate, 200, right? So this can sample up to 100 kilohertz, okay, per channel, which means you have 2 channels. So per channel, you can do 200 to 200. So this is the DAC which you are going to use to interact with real world with LabVIEW environment. So I hope there are no questions. If you have any questions, please feel free to unmute and ask as well. Okay, so in that case, we can continue. So what I'm going to do right now is I have a DAC device connected to my computer. Okay, I have DAC device with me. Okay, so we're going to see how we can connect and configure it. Okay, how to acquire real world data signal into the LabVIEW environment. Right. So first, let us understand what is, already I've explained about MIDAC. Okay, apart from this information, okay, we can also understand that it is capable of acquiring analog input, analog output, digital input and output, audio input and output, power supply, and also it has a DMM device, right? So this is with respect to MIDAC. So I have a MIDAC with me right now with me. So which is USB power, as we spoke about. I connected to my laptop. So once I connected to my laptop, Okay, we have the capability of configuring it, okay, using the NI tools. Okay, once I connected, you can see there is a device like this which has opened. So in order to give a visual, feedback of what device is in front of me, let me try to switch on my camera and show it. Okay, let me just check it. Let me do this by using my okay. For that, I have to stop my screen sharing. I'll stop the screen sharing and let me see my camera adapter. Okay, it is already configured. So let me just turn on my camera. So this is what is in front of me. Okay, I have a. I hope it is visible. So this is the DAC device which I have with me. Okay, this is the my DAC device. Okay, you can see this is connected to my PC's USB cable to my USB port, and you can see that this is the place where I can connect my you know um, sensor inputs or whatever it is. Okay, this is a terminal block. Okay, where I can screw it or unscrew it up. Okay, in order to fasten. Okay, the connections as tight as possible. Okay, I can connect it, and there are certain excitation voltages are also available to it, and there's also DMM available just in case if you want to make medial voltages. Okay, it's low to medium voltage up to 60 volts. You can make measurements. Okay, so that's about it for the and once I make the connection to my computer, you can see that there will be a blue LED which will be glowing. Okay, this blue LED does not indicate power. Okay, specifically, it means that communication between my DAC and my computer has been established. Okay, that's what it means. Once this connection has been made, let me just stop my camera and share my screen again. This is the program which will open up. And to make my job easier, okay, so instead of directly going to programming, okay, I mean, in the sense that directly going to programming is a good thing to do, but sometimes anywhere, okay, most of the time we need to do something called testing, whether our hardware is connected properly or whether the IOs are working fine. Okay, in order to debug it first, okay, in order to run a troubleshooting, okay, there are certain tools available inside NI ecosystem itself. Okay, so basically we can go for configure and test this device. Okay, so this opens something called NI Max. Okay, NI Measurement and Automation Explorer. Okay, which is used to quickly configure and troubleshoot the problems with NI hardwares. Either I can click go, or I can also open. Okay, from here NI Max by going to my uh, start window. So I can open here as well. And you could see that once I open the NI Max, okay, it's just a configuration software. And in order to locate and troubleshoot my information with respect to my DAC hardwares, under my system is where I connected my hardware. So I would find that I will have a list of hardware connected to my PC in this instant. Okay, there are cameras connected. Okay, virtual camera does not exist. It's just a driver. Okay, I have the camera that is my cell phone camera connected, which I showed right now the device, and integrated camera of my laptop. And this DAC has been connected previously, but it's now not unconnected. Okay, it shows whatever device has been connected in the past as well. You can also simulate the instance of hardware as well. Okay, you don't need to even have the hardware, but in order to just run the program and check whether the flow of the application is working fine, okay, you could actually simulate the hardware. Okay, but right now my objective is to understand whether my hardware is actually available or not, which in this case is MyDAC. Okay, MyDAC 2. Okay, as soon as I connect a new hardware to my computer, it will automatically name it, okay, with next number. If I get another background, it will be already automatically named as MyDAC 3. So that's what happened here. So it's an actual hardware with me right now, which I shown you. Okay, so here I have all the easy to configure mechanism available. Okay, there's a self test available, which I can check whether the hardware is working fine or not. There is even a test panel available. Like I could connect some sensors to this ports, and I can do a very quick check. And after making the physical connection using this test panel, I can check whether it is showing the proper value or not. I can take an actual standard voltage generating device. Okay, so let's say generate 5 volts, and check whether it is actually measuring that 5 volts or not. Okay, setting the appropriate pins and everything. Right, so this is just to check the edge device, basically to monitor the edge device. Okay, you can do a lot of stuff, like if you want to know how the pinout works, you have a device pinout option also available. So NI based hardware and software is heavily documented tool. So most of the related help will be available, inside the software itself. Okay, you don't need to. There is absolutely no need to go to, you can say, to internet to check something. Fine. So now that we are okay with this configuration, okay, next important thing is, what are the ways we can acquire the relevant data? Yes, so that is important. So right now, in order to acquire the relevant data, there are plenty of ways to do it. Okay, two ways actually, right? So first way is, either you can go for pre-existing solution. Okay, there are certain tools under NI, okay, where you can acquire data and just display it in a very simple format. That thing you can do. Or second is, you can customize how you want to visualize data. Okay, I'm sure you'll be aware of this second option. Okay, the customization, when customization comes into picture, which means you have to do some programming. Okay, but even with the programming, you can observe the data in a different format. Okay, so let's observe what are these two tools. Okay, first option is essentially, um, to interact with this PC based data auction hardware. Okay, some vendors choose to give something called as soft front panel.
इथं बघू ना शंकर मध्ये
Uh,
कोणतं हे काय
Hello,
आपण इथं घेतलं
someone has unmuted Mr. Sandeep. Oh, okay, thank you. So please do check whether you are unmuted. If you're going to unmute, let me know. I'll give you enough time and you can unmute and ask the question. Okay, there's no limitations. So yeah, so first option is presence of soft front panel. Okay, there will be certain software which will interact with the hardware and present to you in a very generic format. Okay, for instance, this MyDAC hardware has certain software-based instruments, predefined instruments already available. Okay, which can be opened by opening something called instrument launcher. Okay, this will be available once you install a toolkit called as NI Elvis MX. Okay, which I hope would have been shared with you. So once you install it, and once you connect the appropriate hardware, you will get it. Or else you can go to start window and type here Elvis MX. Okay, so if you type instrument launcher here, you will get the option for it. So here you will see certain instruments which are compatible with your PC-based data access. So you might have an idea. You might have asked a question of what is the use of having a PC-based data. Data access is very simple. If you observe my DAC, it will not have a display at all. Okay, if you see the picture of the my DAC, this does not have a display at all. The reason why there is no display in the physical entity is because that will be in software, number one. Number two, you can modify it however you want, depending on the project you're working on. Okay, so here in this case, if you see there is a oscilloscope available. Okay, if you open this oscilloscope, okay, you can see that this is the virtual implementation of the oscilloscope. Okay, front panel of the oscilloscope, soft front panel of the oscilloscope. This is going to be operatable with MyDAC. Okay, here if you see there is a selection options available, MyDAC 1, MyDAC 2. Okay, if you want to acquire from real instrument, my real instrument, if you see this is MyDAC 2 according to my display. And here I can view the data, sensor data or whatever data I'm acquiring. Okay, I can observe it in my computer itself. But in order for this to happen, I need to make physical connections onto my DAC device. So just give me a moment. Let me just take one wire and I'll make that connection. Okay, just a moment. Yes, so now I got wires. So essentially, if you observe the DAC device pinouts, okay, which if I show here, essentially not here. Okay, it's best to go for device pinouts. Okay, analog inputs are essentially a differential connections, just like how an oscilloscope would work. Okay, it requires positive and negative. Okay, we need to have two wires. Okay, to make a analog instrument, analog input measurements. It could be a measurement from a sensor. Okay, but if you want to, if even if it's giving one value output, it needs to be with respect to some other reference, right? So that reference will be given to negative. So that either could be a ground you can connect it to, or sometimes we'll be making potential difference measurement across some resistor. Okay, so in order to make that, you can go for this, right? So it will be a differential measurement is what we call it as. Then analog output, that is the generation part, okay, using MIDAC, okay, will be done by using analog output. Okay, that will be single-ended always with respect to ground. I think someone, I'm hearing someone has unmuted. If you have questions, please let me know. Okay, feel free to ask questions. Okay, so yeah, now we have the hardware with us. Okay, I have the oscilloscope, and in order to generate some signal, okay, instead of generating some signal, what I'm going to do is I'm going to acquire the signal from a temperature sensor, okay, and display it in the oscilloscope. Now, this might sound like it's a very bad idea, okay, but either way, the type of temperature sensor what I have is something called LM35. Okay, so once I make the connection, I'll let you know what I've done. Okay, so essentially I'm using a temperature sensor called as LM35, which is essentially a 3-pin temperature sensor. Okay, to your MIDAC pinouts, okay, you are going to make the connection. Okay, the LM35 requires a 5-volt power supply, which if you see there is if you look at the pinouts, okay, MIDAC has a 5-volt power supply here. So I would just be happy to make the connection over there. Okay, and this LM35 also requires a ground connection, okay, for which I have the connectivity option available as well. And the output, okay, needs to be given to an analog input. Okay, and this negative, okay, unfortunately, okay, should not be left unconnected anywhere. So in order to give a reference, I am just going to give the reference as a ground. Okay, since the sensor is connected to the ground, okay, I'm going to connect it to that also to ground as well, same common ground. So 0 minus is going to be connected to ground. The same ground, whatever ground as the the sensor has been connected. So the connection has been made. Let me just stop my screen sharing and show it via my camera. Okay, so I've used an LM35 connector, and if you see, I already told that there is a 5-volt power supply available on board the data option unit, okay, which I am connecting to my sensor, and ground is also available near it. Okay, so that also is connected to the ground portion of my sensor. Okay, sensor I've connected to the connector pins. Five pin connector pins is there, so I've made use of that. And the very important thing here is how this data from this sensor, the voltage information from the sensor, is reaching the analog input of your MIDAC. So for that also there is a wire available. Okay, the middle wire is available, so which is going to be connected to the analog input 0 plus. Okay, I've connected to that, and minus. Ultimately, I have connected to ground. So I'm going to use an oscilloscope to make a measurement of temperature sensor here. Okay. So the connections has been made. Let us check.
सॉरी
Yes.
एग्जाम का टाइम 2:30 का था, अभी 3 बजने को हो चुका है, 3 बज के चले गए.
I am not aware of exam timings, so we can contact someone else. Thank you. Yeah, so it's fine. So if you see, I have connected it to AI0, and this is where I have to observe the data. So let me just try running this, and I see some voltage. I should be seeing a proper, very straight voltage line. But if it's not coming like that, then there's perhaps a chance that something is wrong.
Sir, your screen is not visible.
Yeah, 1 second. Let me just share the screen. Thank you very much. So hopefully now it's visible.
Yes, sir. Thank you, sir.
Yeah, thank you very much. Okay, I've connected a wrong pin. Just remove this wire. One second. So whatever connections we are making, we have to make sure that we screw it up properly. So which I did right now, and here we are getting some signals. So you can see I'm getting very straight line voltage, and here I can see that I'm getting in millivolts. So 284 millivolts I'm getting, right? So essentially this LM35 sensor, if I'm sure everyone would have heard of such sensor. So it's essentially it measures temperature data and returns it in terms of volts. And how it measures is basically it is whatever voltage value we get, we have to multiply it by 100 to get the absolute temperature measurement. And here we are getting out 278 millivolts. If you multiply it by 100, probably will be getting something like 27 volts. Okay, I mean to 27 degrees Celsius. Okay, 27 degrees Celsius, right? So 27 degrees Celsius is I can assume that my the ambient temperature whatever where I am. Okay, it's 27 degrees Celsius. Okay, but let me just keep my hand on top of it. You could see that it's going to steeply rise. So I kept my hand on top of it and I can sense that it's rising. Once I release my hand, okay, it's going to again fall. Which means I'm connecting the temperature sensor and I'm getting its readings over here. But this is good, it's working. This is an inbuilt software already available to make the measurements. Okay, but is this a really good way to view the data? I mean, it does look good, okay, but there should be a way where we can customize how we observe the data from real world, such that not only we can understand what's happening here, because I know that temperature sensor data is going to return voltage, and I know how to convert it. I mean, you also will be knowing it, but if you want anyone to understand it, okay, so we have to visualize the data in such a way, okay, create dashboards, interactive dashboards in such a way that even a 2-year or 3-year kid looking at the data should be able to understand to its own level. It should be self-explanatory, right? So that's where we go for customization. So if you don't want customization, you can use the existing tools. But if you want to develop something on your own, you want to customize it. If you see this tool, okay, this inbuilt tool itself was developed by using some, like LabVIEW. This whole virtual instrument was itself developed by using LabVIEW, and all the tools here, whatever was listed, okay, was developed by using LabVIEW. Which means if you want to customize it, your good option is to go use LabVIEW. Okay, so using LabVIEW, you can customize to observe data, convert into something which the data you can make sense and display it. Let's see how we can visualize the data in a good format. So I'm sure that you must have already gone for, I mean, yesterday you might have seen how LabVIEW was used. I'll go for new VI. And here you can see the front panel block diagram. Okay, so you must have already gone in depth about LabVIEW programming. Okay, so I'm not going to explain about it again. Okay, we're going to see how to acquire data and bring it inside LabVIEW environment. Okay, we already saw that we can observe the data in the oscilloscope, in the oscilloscope, but how to bring the same data what was observed in the oscilloscope to this particular, front panel or block diagram or whatever it is. So let's get into that. So you have the block diagram, okay, and we have MyDAC already connected to your computer. To access the data from the MyDAC into your computer, into your computer, and as we have already discussed, if you look at the architecture of a DAC system, you have sensor, you have a DAC device, and third one is computer. And the way my computer and DAC device is going to interact is when you connect to the bus, in order to make the communication, first thing you will have the driver software. This driver software makes it possible for communication between DAC device and computer. Essentially, both of them will have a different language. Driver software will act like a translator between them. So this driver software will enable this tool to get data from it and view it in my computer. But once that is done, if you want to develop your own application, okay, to get the data and display it in your own intuitive format, maybe you have some research, you want to display the data in something which can be put into a research paper. So if you want to view the data in such a way, then you have to go for some application software. So that application software, one option is LabVIEW. Okay, apart from that, you have other tools also available, but it needs to be a generic tool. Okay, it needs to have drivers for that. So how do I access my DAC data in my LabVIEW environment? And more importantly, how do I access it with minimal programming, exposure? Let's say yesterday only I started using LabVIEW, and today immediately I am being told to acquire data and make sense of it. That is also a very important, thing to consider. So if that's the case, then NI has certain drivers, okay, which are available, okay, which makes it possible to access the DAC data in my computer itself. Okay, so once you install the drivers, once you install LabVIEW and once you install drivers, okay, you can essentially right click on the block diagram. You can go to measurement IO, and here if you see there is a device, there's a lot of drivers available depending on the type of instrument you're going to access. Okay, so there are thousands of other devices available, but right now we are going to focus on something called DACMX. Okay, because we are going to work on MyDAC, and MyDAC is a type of a DAC device. Okay, this is the driver which is used to access the hardware. And just like programming other embedded tools which you might be familiar with, okay, if you see, we'll be having options like assigning pinouts, read data, write data, assigning sampling rate, start into data, stop into acquiring. All these things also can be done for that, but right now we are not. I mean, yesterday only we learned LabVIEW. It will not may not be possible to learn today itself. Okay, so to use this low level program functions. Okay, let's say you want to first get hang of how to use LabVIEW. Okay, you can experiment with high level programming called as stack assist, where the programming effort by us will be very less, but the effect, the impact will be same. Our objective is to acquire data from external world and bring it inside computer, then later put it into the cloud www and observe from anywhere. So in order to make the process simpler, we have this tool called as stack assist, which I'll pick and place in the block diagram. Okay, I hope there is no question as far as now. If you have some clarifications, please let me know. I'm not sure if everyone has. Oh, okay, it says no longer access to chat, which means no one has access to chat or something. Okay, but anyway, if you have questions, you can unmute and ask. Okay. So if you use this stack assist, in order to make things simpler, you are not going to be asked to do any text-based programming here. Rather, you'll be asked certain questions like acquire signal. Okay, or whether you're going to acquire signal or you're going to generate signal, whether you want to get data or control something. So let's say you want to acquire data. Okay, analog input. Okay, right now I want to acquire analog input. So I'll select analog input. Then next, I'll go for voltage. Okay, even though you might say, okay, there are a lot of other options available here. And there is also temperature also. Since we are working with temperature sensor, why not use this? Yes, that is a good question. But, this particular hardware does not have capability to do temperature acquisition. Okay, this is a very generic data acquisition card, which means it can only acquire voltage data. So I'll select voltage. And this temperature sensor also is going to give you voltage output only, from which you can, choose to do conversion. And as I told that, according to NIMAX, I have a simulated DAC card as well. I have an actual DAC card. The difference here is, if you click on my DAC one, it says simulated, and there is a golden colored USB option. And this is black. My DAC 2 is black, and this says present, which means it's a real hardware. Right now, I have to use a real hardware, which is my DAC 2. And in that my DAC 2, I have to make a selection on where exactly I made the connection. As I already entailed that this is going to be connected to AI0, I'll make the connection there and click finish. Essentially, I can use both of them at the same time, but right now I'm not going to do that because I have only one sensor. I'm going to use it. Here I can, do the signal range. I can set, okay, and do whatnot. Okay, how I want to acquire data. And before actually building the program, I can also do a test. Okay, where is acquiring the data properly or not. Okay, here I can do a self-test here. So I'm acquiring voltage and it's showing me the proper voltage value as well. Okay, essentially whatever is needed for both scientific data acquisition as well as industrial testing and those things, okay, it's available here. If you want to log data inside some file, okay, you have that option also available. Okay, so it's basically not a programming here. Programming is involved, just configuration. What is needed for you is available as options so that you can select it and make it. Now I'm going to just give OK. And it's going to build the program for me. I don't have to build any program. Of course, you can do that if you want higher degree of developer control for you. Flexibility, if you want, you can do. But if you want a quick, this is the way to go. So with very less programming, minimal programming, you're able to acquire data from a sensor and bring it inside the programming environment. And of course, you can just right click on in a terminal. You have an option to create an indicator. Right now, I'll just go for numeric indicator to view the output. And I want this to be done continuously. Okay, when I run this program, it should be running continuously. So what I'll do is I'll just use a while loop. Okay, I hope yesterday the while loop as a topic was been covered. So it will be continuously acquiring the data until I can also set a condition to stop, where I can right click on this. I mean, when you take a while loop, it has a condition to stop. So lab is a graphical program. There is no syntax for while loop to stop. Instead, you have a control to stop the while loop. So if you run this program, you could see that in a programming environment, you bought the data which is to be acquired from this temperature sensor data. Click stop. It's going to stop. You don't want this to run very fast, so essentially you can put a delay as well. And maybe collect the data every 10 milliseconds or so. Okay. So now this is not the actual value, right? This is just a voltage equivalent value. In order to get the actual value, essentially we need to multiply it by 100, which was not possible by using the oscilloscope, right? So now in order to do that, you can essentially, right, you can basically do that in LabVIEW. As you already know, that LabVIEW, in LabVIEW you can do numerical functions, Boolean functions, string functions. Yesterday you might have seen about that. So this is just going to measure the voltage on that pin and return it as a value. Now, in order to make sense of the data, I need to do some calibration. Okay, that calibration is essentially just multiplication by 100. Okay, that can be done in numeric. Multiply incoming value, multiply by creating a constant of 100. So whatever data is measured, multiplied by 100, and that is going to be equivalent to the temperature data. So now if I run this program, you can see that it is returning in terms of temperature. And since LabVIEW is highly customizable, you don't even need to observe this data only as a number. You have an option to use a thermometer. Okay, so LabVIEW has a GUI based controls indicator as well. So if you want to look at temperature data, you look it as a temperature thermometer data itself. Or better yet, if you want to look at with respect to time, if you want to plot the data, you can use a waveform chart. Okay, so that will plot the temperature data with respect to time. So you don't want to go fast, you can basically set some timer and you can see how the temperature data varies with respect to time. If I run this program, you can see that it displays in terms of thermometer it displays in terms of actual actual temperature data. Here it displays in terms of temperature. Of course, here temperature, it will see like it's varying quite rapidly, but there is a small bit of noise over here. That can be eliminated by, there is an option, inbuilt option called auto scaling, which if I disable and say, maximum value is 50 and minimum is 0, you can see this is the, actual temperature data. And if I keep my hand on top of this temperature sensor data, you could see that it will steeply rise. Okay, all three data will be rising. You could observe the inferences over there. If I release my hand, you can see that it's going to fall. So with very quick few steps, I was able to not only acquire data, I was able to convert the sensor data to an appropriate value. I was able to visualize data as a number, or as a thermometer, or time varying instrument as well, in a form of chart. Very few steps, and programming also is not very complex. Okay, so this is how you use LabVIEW for data acquisition. But right now we have seen only temperatures and data. Okay, this could be supplemented not only temperature. Okay, you can go for, if you have appropriate sensor and appropriate signal conditioning units. Okay, you could. There are infinite solutions, infinite possibilities as to what you can connect to a LabVIEW network. Okay, digital sensor, in analog itself we have temperature, pressure, and whatnot. Okay, so there are plenty of options with respect to that. So any questions, please feel to let me know. Or else next what we're going to see is, we are going to see how we are going to transfer this data to a cloud network. Okay, now that we know how to get the data inside the programming environment, okay, this could be a a remote device, okay, which is collecting the data from a certain place. Do you want it to be put inside the cloud? Okay, so using LabVIEW, we know how to acquire data. This is one such solution. Okay, data acquisition hardware is one such solution. We have other solutions inside NI platform itself. Using LabVIEW, you can program an embedded system with IOs as well. Okay, again without any interference from text-based tools. Okay, it's fully graphical. So you can see it up here, right? So once we get this block diagram, okay, once we got the data inside the block diagram, it's up to us on where you're going to transfer the data. But let's understand how to bring this data to a cloud and what are the options available for that. Okay, cloud connectivity options. It depends on several factors. Okay, like what are the options available, what type of cloud you want to access and stuff. Okay, so two options. Number one is either you need to have your own cloud, okay, your own server maintenance, okay, will be there. Okay, using that as a reference, you can build it. But this is going to be very not all the places will have this solution, okay, unless we have the infrastructure available with this cloud infrastructure, network provider infrastructure, everything. If it's available with this, it's fine. Okay, but not everyone will be having access to it. Okay, if not, then you can go for rental basis. Okay, so rental basis means there are pricing options available, subscriptions options available. Okay, using that you can go for, and there are some cloud providers who provide free up to certain usage. Okay, so the LabVIEW support, if you see, okay, there are easy to use cloud support is Google is there, okay, and not so free options like AWS, PTC ThingWorks, IBM, and everything else essentially. Okay, these all support certain cloud-based protocol, and using that you can connect to it. So we are going to see how to do it with Google Cloud. Okay, Google Cloud supports, has something called real-time database, okay, using which you can push data and use it for access from anywhere over the globe. Okay, so we can push the data whatever you collected from here to Google Cloud in real time. Okay, it has very latency in microseconds essentially. So from anywhere over the world you can push the data there, and from anywhere over the world you can collect the data in terms of microsecond latency. And the protocol support is also very easy to use protocols, okay, which means it can be used even in embedded system as well. An embedded system which has operating system which is capable of doing HTTP. Okay, most of the embedded system which has RTOS or operating system running inside it, okay, has the capability of, if it has an Ethernet connection or if it has a internet stack available, okay, it's going to have a HTTP support without any issues. Okay, or at least TCP IP will be there. Using that you can connect to it. Okay, and LabVIEW also has HTTP functions available, okay, using which we can push or get data. Okay. So let's see how we can achieve the same. So now that we have the data from a DAC device, which we, yes, I think I hear someone. I'm sorry. Okay. So yeah, right now we have this program which is capable of acquiring data from actual hardware, calibrate the data, and display it in a sense which could be understood by anyone. Okay, so anyone can understand, okay, if it's measuring thermometer temperature data, it's going to be a thermometer. It's self-explanatory. But this data can only be observed in my computer laptop. Okay, let's say I want to transmit this information to a cloud. Okay, that's why we are talking about. So in that place, we need to have certain functions available in the programming environment as well as options of cloud available. So for this demo, okay, I'm going to use Firebase as the example. So Firebase, why we choose this? It's free to use, and which means you can also in future try it out and develop a tangible application, okay, for prototyping. And if we, of course, if we have some options related to some other paid cloud, you can check for the availability of drivers for that, and that will enable you to that if you install drivers, there's a very high chance that there's going to be getting started get available. Using it as a starting point, you can connect those cloud to the LabVIEW as well. So now I'm going to show you how to configure Firebase, okay, to connect data. So to start it, I'm just going to go to Cloud Console, and here I can see that I have to first configure, Firebase project. I create a project in Firebase to access the data. So I'll create a new project and start a name. Okay, so I'll just enter the name as let me just give a good name for that. I'll just give it as IoT. Okay, so let's not think a lot about that. Okay, I'll create a Firebase project, and it's going to ask whether I need analytics for this. Firebase is not actually a tool which is used for embedded IoT. Okay, embedded data analytics. Okay, it is used for embedded IoT, but analytics will not be with respect to embedded. Okay, meaning like finding anomalies. Okay, with respect to voltage and current is not possible. Okay, Normally Firebase is used for mobile app development, but engineers and scientists have found a way to use this as a tool to transfer data in real time as well. Okay, since it's in real time, we can transfer data. Okay, but the type of analytics it offers is something like how much crashes happened, messaging, okay, remote configuration, predictions with respect to how people use the mobile device. Okay, thus that kind of this is there, which is not required for us. We can disable it safely. So once this is created, I can go for this is the main window, and here what I'll do is I'll go for something called real-time database. Okay, there will be a lot of options. Okay, in IOTT, out of which I'll go for real-time database. This is what is very important. There will be a lot of other options as well. What is of in my interest is I'll go for real-time database, which will help me transfer data from anywhere of the globe. This says store and sync data in real time, and that's what we need. Okay, we should be able to access data across the globe in real time. So I'll create database. Cloud is essentially a data place where the data is going to be stored and accessed. Okay, and that's what is being offered here. And database options is going to be showing as where you want the data to be. And if you consider the latency, okay, so we need to choose something which is very clear, as near as possible for us. So I'm going to go for Singapore, okay, because it's considered to be near, okay, considering the other things. And access, every time someone tries to access it, okay, we need to have credentials to do it. I'll go for start with locked mode itself, okay, which means no one can access it yet. Okay, it says read access, no wrong, write access not available. And what we get here is we will be getting the HTTPS link. When they say HTTP, it will be having a URL through which you can transfer and receive data. Now, in order to create this only, we have gone through these steps. Now, in LabVIEW, we have to build a program, okay, which is going to push this data to cloud through HTTP. So we are already collecting data, and to push this data to cloud, that is at least to Firebase cloud, what we'll do is, I mean, NI programming is a lot of options available, out of which we have to go for data communication, protocols, and HTTP option is available. Okay, so these are the functions used to access the HTTP. So like any LabVIEW program always follows certain steps. Okay, when they are accessing anything. Okay, even in DAC, if you see, in DAC programming, even though there is a function to make everything easier, normally what you'll do is first you'll start, first you create task, then start, then we do read or write. After that, everything is done, we'll stop it and clear it. So there is a specific sequence to access the hardware. For every operation in LabVIEW, okay, there is certain sequence. Like for example, this HTTP, always you have to start with open handle. And I'm putting this outside the while loop because it needs to happen only once. What this does is it creates a reference for HTTP, like out client and how it will be created. And After this process is done, the HTTP this data transfer process is done, we have to close the handle, and that need not happen inside. We can put this inside. So these two things should happen only once. Okay, this is like initialization, and this is like cleanup. What should happen continuously is put. But in order for this put to happen, first we need to open it at least once and push the open reference from outside to inside. And once this total, if once I click stop, once I click the stop, I need to close that reference as well. So I'll pause the data as well. Okay. I'll copy this link to which I can get the data over here. And you might ask, where should I paste that? That will be pasted in this input called as URL. I'll right click on this URL input, create a constant, and paste it over here. And this is where the things get a little bit, complex. Not really complex. A little bit of steps will be there. Okay, so we need to tell to the compiler what type of, we need to tell to the Google, since we are giving the HTTP, we have to tell what type of data we are transferring to the HTTP. Okay, so this is going to be temp. And what format we are going to transfer data is, not all the formats are possible. Okay, so essentially this Firebase is a database, and it's a database called as NoSQL database. Okay, the way the data is getting stored is actually a format called as JSON. Okay, JavaScript Object Orientation. Okay, so we need to send whatever data we send, we need to send it in that format. So whatever data you're sending, the name .json. And this is the data we are sending. The data cannot be just directly connected from here to here. It doesn't work that way. So again, we need to go for certain steps. So the certain steps is going to be, first we need to extract the data from this, data type. Here, the blue color data type is something called dynamic data type. Okay, which is unnecessary data type for us. Okay, I just need this data type as a, a scalar value. To extract such data in LabVIEW, there is something called express functions, signal manipulation. I have something else from DT function, okay, which I'll make use of. Here, there is an option to convert from dynamic data type to a scalar data type. Okay. And this data type also, even though it's a scalar, this scalar is actually a data type called as numeric in LabVIEW. And this data type buffer is actually a data type called a string, which if I try to connect, will not be accepted. So what I need to do is, as I already told you, Firebase accepts only a data type called as JSON. And in order to convert whatever data you have, it is JSON. In other programming tools like Python, okay, we have to import something called as, JSON package and do some complex conversion. Okay, it's a simple conversion there only. Similarly, in LabVIEW also, there is something called toJSON option available. Which is essentially will give us the JSON string data, which you can connect it. And to this input, it says connect anything. But in fact, you cannot really connect anything. It only accepts something called as clustered. Okay, so whatever data type you have to have it as a cluster. So to convert anything to cluster, we use something called bundle. So the scalar we connected to input, and this to inside here. So once we run this program, it appears as though you are sending the data, everything works fine. Here, I'm collecting the data, real-time data from the data action hardware and pushing it into the cloud. But if you come over here and look, there will be no reflection as to what is happening. That is because if you see, lab program is working fine. Okay, there's no problem with that. But if you go to rules, it says that read permission is also false, write permission is also false. Basically, data transfer does not happen. So what I will do is I have to make this as true. Publish. Now again I run this program and come back to my dashboard in Firebase. You can see that there is a data which is appearing over here. When I keep my hand on top of it, you can see the temperature data is appearing over here. So you can basically, get data into IoT platform like this. So this is how we implement IoT based systems from data action level to cloud level. And later on, if you want to get back the data into lab environment, instead of using put, you can use another function called get, and you can get the data anywhere over the world. Okay, so I can push the data from Bangalore, and I can access the data in, let's say, Los Angeles, or in Germany, somewhere in Germany you can access data, and in Japan you can access data only by using this link. Okay, such is the power of cloud infrastructure. So if you have any questions, please let me know. Any questions? Any clarifications? Fine. So yeah, fine. In that case, it's not like you have to use only analog sensor data, as already explained. Okay, you can also acquire data from a digital data as digital sensor as well. Okay, not only can you get data from a digital sensor. Okay, you can essentially control something of digital channel as well. So one of the things which are going to change is in, in this DAC assistant you can remove up to this. Okay, everything you can remove. So depending on the DAC hardware, okay, if it has a DIO in it, you can just use DAC assistant only to program analog or digital. Okay, one thing is going to be just DAC assist, and instead of um, analog, you're going to go for digital. Okay, if you're going to go for multiple, pins, bunch of pins, you can go for port. If you're going to use only one pin, you can go for line. And I'm going to choose something which is already available. And here you go. Only one pin I have selected. I can give OK for that. So I'll get the digital data instead. Okay, here I'm getting the Boolean data. Unfortunately, this Boolean data will not be only a single value. It will be an array of value, out of which I can choose to extract only one value. Then I can choose to connect it to the cloud just like that. Okay, so I can choose to name it as a digital. And I go back to the console, you can see that there's a Boolean data now. Okay, not only can you acquire that Boolean data, you can also connect it to an appropriate sensor. Okay, just give me a moment. Let me just quickly connect it to a sensor, and I think it will be good to go. Okay, as I already shown, my DAC also has digital pins, 8 in fact. So if you have to make connection to that, it's fairly easy. Okay, right now I'm just going to connect it to an appropriate switch. Okay, that is DA0. This is going to be connected to a switch. Okay, it need not be a switch. Okay, it could be anything. Okay, so if you see I'm connecting it to if I'm pressing the switch, it's going to show true. If I release the switch, it's going to show false. Okay, so whenever the value changes, it's going to show true, false, whatever. So any questions, please let me know. Also, of course, you can observe how much data is getting transferred or received. Okay, you can see there is something called usage available. So far, if you see, since the program is running continuously, it has used around 479 KBs. Okay, this is very less, but sometimes we'll pass image data also and all. Okay, it may go around the MBs also. Okay, sometimes we'll be passing high amount of voltage, channels. Okay, so it might go in GBs or sometimes in TBs per month. So any questions, let me know, or else we can conclude the session. Any questions? Anything in particular? So if not, this is my contact information. If you have any technical queries or anything with respect to implementation, proof of concept explanation and stuff, okay, you can just contact me. I'll be able to guide you as much as I can. So if there are no doubts, okay, you can just let me know. I'll paste this into the chat box.
Participants, if you have any questions, please free to ask.
Yeah, thank you everyone. In that case, I will stop sharing the screen. If you have any questions, you can ask, or else thank you very much, ACS College of Engineering, for giving me this wonderful opportunity. It's been a pleasure to be a part of this FTP program, to share my knowledge, such that if I teach the students, okay, it's just going to stop with that. But I'm sure that since it's an FTP, if I share my insights to this, okay, this could go to potentially thousands of students, and it could help in the enrichment of the society much more. So thank you everyone. And in that case, I'll over to you,
Information
ma'am.
shared with participants. Thank you very much. Dear participants, now I am sending the link for today's attendance and feedback. Please fill the feedback and send. So 1 second, I am sending. So now I am ending the meeting. Please fill the feedback and attendance, this one which is there in the chat box. Thank you. Thank you very much for participating. And thank you, sir. Thank you for your valuable information given in the lab.
Thank you, ma'am.
So I am ending the session.